and synthetic biology are
Yes, he's even more imaginative than the people who invented singing.
Longest for the longest time. Whoa, longest for the longest. If you said goodbye to me tonight.
Yes, he's even more imaginative than the people who invented singing.
Em ấy cái nào long em eron nan quan vậy vậy dân công an chuan cho chuan pam men train chuan pam yon pugin mi pa America en bagen ka yorba de.
Now then, James, tell them, please, that the United States government now wants to turn this great destructive power into something for the benefit of mankind. And that these experiments here at Bikini are the first step in that direction.
Yo que na pa que yang rutora que me chapkan en malalaga que me con que me chaye ta we na como no mani ngani que riba como no puedo ver en pillai como a que me chaye copan cherbal chabo chabai no que como no akan lele que copan ai de no como eren porque y me arjar pulai ram kanan ka wewen na magad gitu.
Crossroads, scene 25, take 1.
Well, now then, James, will you tell them that the United States government now wants to turn this great destructive force into something good for mankind, something good for mankind, something good for mankind.
All right, is that all?
Okay, got it.
Hoy doy no.
Destructive.
I thought it was great. I thought it was one of the greatest things I've ever seen. And it was, really. Being from the country, of course, I would have never had a chance to see anything like that in my lifetime.
Hold you!
practicing it for many years.
And synthetic biology are coming up now a lot more. And I'm Christina Agapakis, and I am now a lot more. Coming up now a lot more. And there's a lot of people working on making sort of biological circuits in these also.
Can you tell us what exactly?
No, they basically announced that the J. Craig Venter Institute has synthesized the whole genome of a bacteria and used that. And there's a lot of people working on making sort of biological circuits, and so.
Okay. So the genome that they're using, they made it up?
No, they used a naturally occurring sequence, and just sort of remade the natural sequence synthetically. But the biological circuits, and so.
Okay.
They did.
So the genome that they're using.
Of biological circuits, and so.
Okay.
Wow.
So the genome that they're using, sort of know a little bit about that's recombinant DNA technology. What's different between this and what you would do if you were cloning a bacterial cell?
I think the main difference is scale.
Okay. So the genome that they're using.
Functioning bacteria, but in this case, it's I don't remember the quote exactly, but it's something about from life to life.
Okay.
Wow.
So the genome. Okay. So what's the next step? I mean, this is they've got a colony of cells going that has their DNA in it that they designed. Okay. So what's the next step? What happens?
Well, these cells, they have
Okay. So the genome.
you could make a different code basically by if you can synthesize it yourself on a computer and then put it to bacteria, that bacteria start making it. Synthesize it yourself on a computer. it is a sort of new platform for development. So I never really think about genomes. I think about sort of enzymes and pathways a lot more.
Right. I thought of synthetic biology before I looked up.
People who are working on making medicines and tools and bacteria, medicines and sort of as make a lot of things. That's where I think the medicines and tools and bacteria sort of as a way to much bigger or smaller, just different ones.
Right. I mean, so your basic recombinant DNA technology, from the 1980s is you take a gene from something that already works, and you put a little bit of bacteria, and it makes the product. Yeah. And synthetic biology is something different because you get to
I think that a lot of, there really is
Humans, like chemicals, are really all about bonds. Think about all the relationships in your life. You're a casual acquaintance to some people, a colleague or friend to others, and maybe more to that someone special. Maybe you're dating someone casually, or you're in a committed relationship, or you're married. There are all kinds of different combinations of people out there. And sometimes, people fall for a vampire or a werewolf. Who am I to judge? Fact is, each type of relationship requires different things from you and the other person. But if you play your cards right, these relationships allow you to relax and escape the stresses that come with the constant search for affection. Distance is important in relationships too. Of course, too much distance makes it hard to stay focused on each other and requires a lot of effort to keep things together. And I may not have to tell you, too little distance can be a problem as well. Everyone needs their space, and when you don't have any, you just end up pushing away from whatever's crowding you. In this way, atoms are a lot like us. We call their relationships bonds, just like we do with our own relationships. And there are many different types. Each kind of atomic relationship requires a different type of energy, but they all do best when they settle into the lowest stress situation possible. The nature of the bond between atoms is related to the distance between them, and like people and vampires and werewolves, I suppose, it also depends on how positive or negative they are. The difference is that unlike human relationships, we can analyze exactly what makes different kinds of chemical relationships work, and that's what this episode is all about. But people, please remember that we here at Crash Course do not dispense relationship advice. First things first, why do atoms do this at all? Well, like everything else in the universe, atoms do whatever they can to reduce their overall energy. And they reach their lowest energy by achieving a balance between attractive and repulsive forces, being neither too clingy nor too aloof. So when two atoms approach each other, the electrons of each are attracted to the protons of the other. This is the electrostatic force. Like charges repel, opposites attract. Like in real life, or at least Paula Abdul songs. I know, I'm old. So when one atom is attracted to another, just like Edward Cullen and Bella in chemistry class, to use a slightly more timely reference, it gets stressed out by the attractive force and tries to relieve the stress by getting closer. We've all been there, right? That hot, nerdy vampire girl in your chemistry class, it's intense. The pull is so strong that the stress level or energy rises when the two are separated, so they stay close. But sometimes they can get a little too close. When that happens, the nuclei repel each other because of their like charges, and the energy between them rapidly increases, and they both back off just enough to find that perfect little distance between them, and everyone relaxes. This ideal, wonderful distance is the bond length. It's the distance between two nuclei at the point of minimum energy. In other words, where the attractive and repulsive forces cancel each other out. The distance at which these two atoms of chlorine reach their minimum energy, caught between the attraction of the electrons to the nucleus and the protons repelling the nuclei, is the bond length. That energy minimum, which we know absolutely is negative 239 kilojoules per mole, occurs when the distance between the atoms is 0.00199 nanometers. That distance is the bond length of Cl2, chlorine gas. Now, because the electrons are attracted to both nuclei in the molecule, they actually spend the majority of their time in the space between them. This is often described as sharing electrons, and we call this kind of bond a covalent bond. But not all sharing is equal. I should know, I have an older brother. The strength with which an atom holds shared electrons is called its electronegativity. The electronegativity of various elements are all super well known and waiting for you in tables on the internet. If two atoms in a bond have very different electronegativities, like say hydrogen at 2.1 and oxygen at 3.5, the electrons are more attracted to the atom with the higher electronegativity. The difference is so great that the electrons spend most of their time around the stronger atom and much less time around the other one. Like how all the neighborhood kids wanted to hang out with John, my older brother, because he was more charismatic. When the electrons hang out closer to one side of the bond, it creates a slight negative charge in that area and a slight positive charge around the other atom. This separation of charges is called polarity. And it's the polarity of the molecule that these atoms form, H2O, that makes water the most important molecule on Earth. Covalent bonds like this, where electrons are attracted to one atom more than the other, causing a separation of charges, are called polar covalent bonds. But when a covalent bond forms between two identical atoms, like the two chlorine atoms in our graph earlier, the electrons are distributed evenly. We call this a nonpolar covalent bond. But you've also got to consider the middle option, where the atoms aren't identical but have very similar electronegativities, like unlike hydrogen, with an electronegativity of 2.1, and sulfur at 2.5. The difference here is so tiny that the electrons are pretty much still evenly distributed, and we call that a nonpolar covalent bond as well. There's a huge world of important chemicals that have these kinds of bonds, so many, in fact, that we will dedicate a couple of separate episodes to them. Covalent bonds tend to form from nonmetals and sometimes metalloids, those elements that have both metallic and non-metallic characteristics. That's because most of them hold their electrons so tightly that they're more likely to share them with another atom than to gain or lose them altogether. Metals, on the other hand, have loosely held outer electron shells, so they're constantly dropping electrons and becoming positive ions. And when positive ions come across negative ions, like those formed from halogens, for instance, you have to know what's going to happen. They're attracted to each other, which means energy is required to keep them apart, which means that they're gonna bond if they can, creating that oh-so-wonderful point of minimum energy. This type of bond is unsurprisingly called an ionic bond, a bond formed between a positive ion and a negative ion. Because the ions are formed when one atom loses electrons and the other gains them, we often say that an ionic bond is formed by the transfer of electrons from one atom to another. And we can calculate the amount of energy that exists in a bond between ions at a given distance using a formula called Coulomb's law. Note that this only works for ionic bonds because the calculation requires